Unlocking the Power of Bioelectricity, a new frontier in regenerative medicine and beyond. In the realm of biomedicine, a paradigm shift is underway. This shift focuses on a concept that transcends the traditional understanding of cellular processes, emphasizing the role of bioelectricity as a fundamental force in shaping life itself. Bioelectricity, the electrical signals that govern cellular communication and organization, is revealing itself as a key player in everything from embryonic development to tissue regeneration and cancer treatment. This blog post delves deeply into the world of bioelectricity, exploring how it serves as the software of life and holds the potential to revolutionize our approach to medicine. The Foundation of Bioelectricity. Bioelectricity is not merely a byproduct of cellular activity. It is an essential language that cells use to communicate and coordinate their actions. This bioelectrical communication network enables cells to form complex structures, maintain physiological states, and define the boundaries between the self and the external environment. Unlike genetic or biochemical pathways that have long been the focus of biological research, bioelectricity offers a more dynamic and integrative view of how life is organized and maintained. At the heart of bioelectricity is the concept of voltage gradients, differences in electrical potential across the membranes of cells. These gradients are established and regulated by ion channels, which control the flow of charged particles like sodium, potassium, and calcium into and out of the cell. The resulting electrical signals are shared among neighboring cells through structures known as gap junctions, forming a bioelectrical network that spans entire tissues and organs. This network is not limited to the nervous system. It is ubiquitous throughout the body. Every cell, whether it is a neuron, muscle cell, or even a simple skin cell, participates in this bioelectrical conversation. These electrical signals are crucial for determining cell fate, guiding tissue development, and ensuring that cells work together to achieve common goals. Cellular collective intelligence, the power of the group. One of the most profound implications of bioelectricity is its role in enabling cellular collectives to function as intelligent agents. Traditionally, cells have been viewed as passive components, following genetic instructions to carry out specific tasks. However, bioelectricity reveals a different picture, one where cells are active participants in a collective decision-making process. This collective intelligence is evident in various biological processes. For example, during embryonic development, a single fertilized egg cell undergoes a series of divisions and differentiations to form a complex, multicellular organism. This process requires cells to communicate with one another, share information about their surroundings, and make decisions about their fate. Bioelectric signals play a crucial role in coordinating these activities, ensuring that the developing organism takes on the correct form and function. This idea of cellular intelligence challenges the traditional notion that development is a deterministic process, solely driven by genetic programs. Instead, it suggests that cells are capable of problem-solving and adapting to changing conditions. This adaptability is crucial for processes like wound healing and tissue regeneration, where cells must work together to repair damaged structures. The journey from single cell to complex organism bioelectricity in development. Embryonic development is one of the most remarkable journeys in biology. It is the process by which a single cell, the fertilized egg, gives rise to a complex organism with multiple tissues, organs, and systems. This journey is guided by bioelectric signals that communicate target states, essentially the goals that the cellular collective is working to achieve. One of the most fascinating aspects of development is the ability of cells to navigate what is known as anatomical morphospace. This conceptual space represents all possible configurations of an organism's anatomy. As cells divide and differentiate, they move through this space, guided by bioelectric signals that help them reach the correct anatomical configuration. This process is not as rigid as once thought. For example, if an embryo is cut into two halves, each half has the ability to regenerate into a complete, normal organism. This phenomenon, known as regulative development, demonstrates the remarkable flexibility of the bioelectric communication network. It also highlights the importance of bioelectric signals in ensuring that cells can adapt to different starting conditions and still reach the correct anatomical outcome. The implications of this adaptability extend beyond embryonic development. It suggests that the same bioelectric principles that guide development can also be harnessed for regenerative medicine. By understanding and manipulating these signals, it may be possible to induce the regeneration of lost or damaged tissues in adult organisms. Bioelectricity serves as a cognitive glue that holds together the collective intelligence of cells. It allows cells to maintain pattern memories, stable electrical states that represent specific anatomical structures or physiological conditions. These memories are crucial for ensuring that cells work together to achieve and maintain the correct form and function. One of the most compelling examples of bioelectric memory is seen in the process of regeneration. Certain animals, like salamanders and planarians, have the remarkable ability to regenerate lost body parts. This ability is not just about growing new tissue. It requires the cells to remember what the correct structure should be and to coordinate their actions to rebuild it. In the case of the planarian, a type of flatworm known for its regenerative abilities, researchers have discovered that bioelectric signals play a critical role in determining the number and shape of body parts. By manipulating these signals, scientists have been able to induce planarians to regenerate with 2 heads instead of 1. Remarkably, this altered bioelectric state is stored as a memory, meaning that even after repeated amputations, the worms continue to regenerate with 2 heads. This example highlights the power of bioelectricity in shaping not just the form of an organism, but its very identity. It also underscores the potential for bioelectricity to be used as a therapeutic tool for correcting developmental defects and promoting tissue regeneration. One of the most exciting possibilities of bioelectricity is the ability to rewrite the biological set points that guide cellular behavior. These set points are essentially the target states that cells work to achieve, whether it's a specific anatomical structure or a physiological condition. By decoding and altering the bioelectric signals that define these set points, it may be possible to direct cells to regenerate lost tissues, correct developmental defects, and even combat cancer. This approach represents a significant departure from traditional molecular medicine, which focuses on manipulating genes and proteins to achieve desired outcomes. Instead of micromanaging the molecular pathways that govern cellular behavior, bioelectricity offers a way to reprogram the entire system by changing the signals that cells use to communicate. For example, in regenerative medicine, researchers have successfully used bioelectric signals to induce the regeneration of limbs in amphibians. By manipulating the bioelectric signals in the cells of a frog embryo, scientists were able to guide the cells to regenerate a lost limb. This approach does not involve the introduction of new genes or proteins. It simply involves altering the electrical signals that guide cellular behavior. The potential applications of this technology are vast. In addition to limb regeneration, bioelectricity could be used to promote the healing of wounds, repair damaged organs, and even regrow entire organs. It also offers a new approach to cancer treatment, where the goal is not to kill cancer cells, but to reprogram them to return to their normal, healthy state. The implications of bioelectricity extend far beyond traditional medicine. The future of biomedicine may resemble a form of somatic psychiatry, where the focus shifts from chemistry to the semantics of cellular communication. This new paradigm would involve understanding and manipulating the informational content of bioelectric signals to guide the collective behavior of cells and tissues. In this future, medicine would be less about delivering drugs and more about reprogramming the bioelectric networks that guide cellular behavior. This approach would offer a more holistic and integrative way of treating diseases, addressing the root causes rather than just the symptoms. For example, in cancer treatment, the goal would not be to destroy the tumor with chemotherapy or radiation, but to reprogram the bioelectric signals in the tumor cells, convincing them to return to a healthy state. This approach could reduce the side effects of traditional treatments and offer a more effective and lasting cure. Similarly, in regenerative medicine, the focus would be on guiding cells to rebuild lost or damaged tissues by providing them with the correct bioelectric signals. This approach could lead to more effective and efficient tissue regeneration with fewer complications and better outcomes. The interplay of bioelectricity and immunity is, well, quite fascinating. Bioelectricity also plays a crucial role in immune function, influencing how the body responds to infections and other immune challenges. Studies have shown that manipulating bioelectric signals can enhance the body's ability to fight off infections, offering a new avenue for boosting immunity and combating diseases. One study, for example, found that hyperpolarizing tissues, altering their bioelectric state, could improve the survival of embryos challenged with pathogenic bacteria. This effect was mediated by changes in the bioelectric state of the tissues, which influence the activity of the innate immune system. This finding opens up new possibilities for using bioelectricity to enhance immune function and treat immune-related diseases. It also highlights the interconnectedness of the body's systems, with bioelectric signals influencing not just cellular behavior, but also immune responses and overall health. Cancer as a bioelectrical disorder, rethinking tumorigenesis. One of the most intriguing applications of bioelectricity is in the treatment of cancer. Traditionally, cancer has been viewed as a genetic disease, driven by mutations that lead to uncontrolled cell growth. However, bioelectricity offers a different perspective, suggesting that cancer may be more accurately described as a bioelectrical disorder. In healthy tissue, cells are electrically connected to one another, forming a cohesive collective that works together to maintain the correct structure and function. However, when cells become disconnected from this bioelectric network, they lose their sense of identity and revert to a more primitive, single-cell state. This loss of collective identity is what drives the uncontrolled growth and invasion that characterize cancer. By restoring the bioelectric connections between cells, it may be possible to reprogram cancer cells to return to a healthy state. This approach does not involve killing the cancer cells, but rather convincing them to rejoin the collective and resume their normal functions. For example, researchers have found that by co-injecting ion channels that promote bioelectric connectivity, they can prevent the formation of tumors even in the presence of oncogenic mutations. This finding suggests that bioelectric signals play a critical role in maintaining cellular identity and preventing the development of cancer. Bioelectricity and the microbiome, a new perspective on host-microbe interactions. The relationship between bioelectricity and the microbiome, the community of microbes that live in and on the human body, is an emerging area of research with profound implications for health and disease. Studies have shown that the microbiome can influence the bioelectric state of its host, affecting everything from development to immunity and even behavior. For example, researchers have discovered that certain bacteria can alter the bioelectric signals in planarians, a type of flatworm, causing them to regenerate with abnormal structures, such as two heads. This finding suggests that the microbiome can exert a powerful influence on the bioelectric state of its host, potentially affecting its development and health. This interplay between bioelectricity and the microbiome offers a new perspective on host-microbe interactions. It suggests that the microbiome is not just a passive participant in the body's processes, but an active player that can influence the bioelectric signals that guide development, immunity, and even behavior. Understanding this relationship could lead to new approaches for treating diseases and promoting health. For example, manipulating the microbiome to restore normal bioelectric signals could be a strategy for treating developmental disorders, immune diseases, and even cancer. Hacking the software of life, the future of bioelectricity in medicine. As our understanding of bioelectricity deepens, the possibilities for its application in medicine continue to expand. The concept of hacking the software of life, reprogramming the bioelectric signals that guide cellular behavior, holds immense potential for transforming healthcare. One of the most exciting aspects of this approach is its versatility. Bioelectricity is not limited to a specific type of cell or tissue. It is a universal language that all cells use to communicate. This means that bioelectric interventions could be applied to a wide range of conditions, from developmental disorders and regenerative medicine to cancer treatment and immune modulation. For example, in the treatment of birth defects, bioelectricity offers a way to correct complex anatomical structures by restoring the correct bioelectric signals. This approach could be used to repair defects that are currently untreatable, offering new hope for patients with severe congenital conditions. In regenerative medicine, bioelectricity could be used to guide the regeneration of lost or damaged tissues, reducing the need for transplants and improving outcomes for patients with chronic injuries. This approach could also be applied to aging, where the goal would be to restore the bioelectric signals that maintain tissue health and prevent degeneration. In cancer treatment, bioelectricity offers a new way to combat tumors by reprogramming cancer cells to return to a healthy state. This approach could reduce the side effects of traditional treatments and offer a more effective and lasting cure. Finally, in immune modulation, bioelectricity could be used to enhance the body's natural defenses against infections and other immune challenges. This approach could lead to new treatments for immune-related diseases and improve overall health and well-being. A new era in medicine. The study of bioelectricity is opening up a new era in medicine, one where the focus shifts from treating symptoms to reprogramming the fundamental processes that govern life. By understanding and manipulating the bioelectric signals that guide cellular behavior, we can unlock new possibilities for treating diseases, promoting health, and extending life. As we continue to explore this frontier, the potential for transforming healthcare is immense. Bioelectricity offers a holistic and integrative approach to medicine, one that addresses the root causes of disease and promotes the body's natural ability to heal and regenerate. The future of medicine lies not in the chemistry of life, but in the software that drives it, the bioelectric signals that make us who we are.